My name's Ian Smith. I'm the Technical Content Manager at MIPI Alliance, and I'll be your moderator for today's session. Pleased to say we've got some great speakers lined up for the session today. We've got Tim McKee, the MIPI I3C Working Group Chair, Matthew Schnorr, MIPI I3C HCI Subgroup Lead, and Michele Scarlatella, I3C Technical Consultant to MIPI Alliance. So a couple of things, housekeeping items just to mention before we kick off. Firstly, all audio lines will be muted on entry. Today's session will be recorded and will be made available on the MIPI Alliance website under our knowledge library. We aim to do that by the end of today. Let's just quick look at the agenda. So we've got four parts to today. 3 presentations, which should take around 45 minutes, followed by a 15-minute Q&A session. We'll kick off with Tim, who will give a update on what's new with I3C and I3C Basic. We then have Matt talk about what's new and what's latest with the host controller interface. And then finally, we'll have Michele present on how I3C enables power efficient designs. So hopefully 3 really interesting sessions lined up. For the Q&A session, please submit your questions via the chat window or the Q&A panel. You can submit your questions as we go through the presentation or save them up till the Q&A session later on. Okay, so that's our plan for today. I'd like to hand over now to Tim to take us through the first presentation. Thank you, Tim.
Awesome. Thank you, Ian, and welcome everybody. Glad to have you on board today for our webinar. Oh, wrong way. So I'm here to talk to you about what's new with I3C and I3C Basic. As many of you know, if you're new to I3C, I3C was created because the sensor market is growing tremendously, and devices we're now seeing with many more sensors, sometimes upwards of 20 sensors on a device. And so in order to enable this ecosystem, we created I3C as a scalable and cost-effective interface targeting mobile, IoT, automotive, and transportation, all of these areas in which sensors are really prominent right now. Some of the great things about I3C is reduced pin count, support for low power, high speed communication, low complexity, still keeping targets under around 2,000 gates, and still we preserve backwards compatibility with I2C. If you've been following I3C over the years, you know I3C has gone through some changes. Ever since we launched the initial version of I3C 1.0 back in 2016, a few years after, I3C Basic, a license-free subset of the I3C spec, was released in July of 2018. From there, we wanted to revamp our specs. We started creating a 1.1 specification, and that was released with new features for the full version of I3C back in 2019. Now, as all of you know, 2019, the end of 2019, started some challenging times, and we've met with some challenges here in the workplace. And so, though we were expecting to release the I3C Basic version 1.1 to synchronize with that middle spec, delays, all sorts of complications came, and we ended up pushing it out. And so now, here in 2021, we have 2 new specs, the I3C V1.1.1 and the I3C Basic 1.1. They're very closely aligned. The full spec doesn't really have major features. It was more clarifications. We wanted to clean it up. We wanted to get everything, the feedback, a lot of stuff in there. And then we knew I3C Basic, we wanted to be a subset again. And so those are now synchronized, and we're very excited to have those 2 new specs out and churning now. So key features, why do we think I3C is so great? Well, we created it to be a fast and efficient communication channel, multi-drop 2-wire interface with a max clock rate of 12.5 megahertz, and different voltages supported, anywhere from 1.2 to 3.3 volts. And in fact, Basic can support even down to 1 volt operation. We also have new line codings. Not only do we have the standard data rate, but now we've added high data rates and multi-lane capabilities as well. There's also advanced features. So this isn't just a 2-wire simple bus. Maybe if you're thinking back to I2C or something like that, we've added a ton of advanced features. In-band interrupts with qualified information, hot join, device resets, error detection, a lot of the things, the tools that modern bus designers want. On top of that, system management is a big part. We now not only can have a main host controller, but there's ability to have a secondary host controller. Dynamic address assignment and group assignment. Group addressing is huge, allowing for much better efficiency on the bus. And like I mentioned before, we've done all of this while still maintaining backwards compatibility. In fact, I2C operations can continue, and fast operations can be considered invisible on the bus due to the implementation of a 50 nanosecond spike filter. And so it allows I2C and I3C to work together on the same bus, which is phenomenal. So if we're looking at what these new specifications include here in 2021, as I stated, the new full version of I3C is mostly clarifications, typos. We had a big terminology change, and then of course incorporation of all of the previous changes. If you're familiar with things like target reset, the white paper that we created, that's now been incorporated into the specification, so it's a whole document now. Now the basic version, that has been revved all the way back from the 1.0 revision. And so not only did we have clarifications, errors, typos, terminology changes, but we also pulled a lot of new features and added that into I3C Basic. You can see here on the right side with this comparison and features table, on the left, we have our version 1.0s. On the right, we have our version 1.1.1s, and you can see with the green check marks, there's quite a few new features enabled in these new specifications. So there's a lot to learn about. Another thing we're very, very excited about is that other industry partners are using I3C. JDEC, one of our first liaison partnerships, we helped create the Serial Presence Detect, or SPD, hub for DDR memory. And so we created a great partnership and have delivered and continue to deliver with JDEC on that. One of our newer partnerships was with the DMTF, where we created a Management Component Transport Protocol, or MCTP, over I3C binding. If you are familiar with I2C, you might have heard of the I2C binding spec for MCTP. We realized how useful that was and wanted to advance that and create that for I3C as well. And so that was released earlier this year. On top of that, we're working with other partners as well: PCIe, IEEE 1722, protocol adaptation layer for I3C over PAL, ETSI, and we want more. We are seeing the uses of I3C. We're seeing industry partners see the value in it. We want to see what else I3C can do, and a lot of that is ideas from other people in the industry. What do you think? How else can we use I3C to benefit the economy or the ecosystem? And of course, we don't just do the specifications. With these specifications, there's always support. And we wanted to be there to make sure that implementers knew. We were there to help them and make sure that this technology succeeded and was good to implement for implementers. So we created a CTS, a conformance test suite, so that there are a set group of tests that implementers can run and know that if they're passing these tests, that the chances of them being able to interoperate with other devices is very high. We have the host controller interface, which I'm excited for Matt to talk about later, which is on the software side, really standardizes the software side. We have the kernel module for Linux, debug for I3C as a separate specification, Disco for I3C. The work group for I3C has also created FAQs and application notes to really aid and help implementers as they're building this technology. So there's tons of information on I3C, and we also have other resources. Of course, there's the work group that we meet weekly. And we want people to get involved, right? Whether that's sending feedback, letting us know how your implementations are going, you can email us, or coming and visiting and participating in the work group itself. So with that, I'd love to pass it on to Mr. Matt and hear him talk about our HCI host controller interface.
Tim, welcome everybody. So I want to talk about the host controller interface briefly here. I want to share with people why this is important, why MIPI is trying to standardize the host controller interface and encourage people to use it, and what we're going to try to do with it and what value it brings to the I3C ecosystem. So what is it and why are we doing this? We want to standardize the interface that platform software uses because this helps to save time for integrators and developers, and especially people trying to build software stacks on top of I3C. We think this is going to provide a rich ecosystem for people to develop, especially emerging use cases, especially IoT and sensors, mobile sensors, of course, because that's where I3C began, data centers, because we're seeing this build up for data center applications. You saw some of Tim's use cases earlier about PCI Express, DDR memory, and other emerging applications. And we want people to come tell us, this is where we want to build, and these are the type of things we want to use this for. But the host controller interface is going to be a foundational part of what this can do. So the key part of all this is a good standardized command response interface where your host software, the system bus, can put in commands and get responses back from the bus. And the host controller, the hardware or the logic unit that's actually doing this work for you, can control the bus, can issue the commands, can see the responses, can sense inbound interrupts coming over the bus, and provide these to you with well-documented data structures and things that are designed for you. And as developers, you don't have to go reinvent those wheels. You don't have to go recreate those things from scratch. And this really gives people the ability to use common software drivers. Tim mentioned the Linux kernel driver that was being mentioned before. This is a key foundational piece of this. As MIPI actually was able to create this Linux kernel driver, submit it to the ecosystem, get it approved, and mainline into the Linux kernel tree. This is a huge thing. And this also embodies the common register definitions, the common data structures, and does the operating modes and abstracts those to make sure that anybody who implements a standard device in the hardware can have it supported in Linux and potentially other RTOSs that can use this as well at any level. So really, application developers can take this, build on it, and focus their attention on what's more important, which is the higher level flows. Like, I need to do these types of transfers, these types of things for command response flows, and I need to get these kind of inbound interrupts off the bus. All you have to worry about is linking to it and using the data structures, and the hardware does the work for you. Now, we also realized that we couldn't just have a fixed limited set of capabilities. So HCI spec also defines extended capabilities where driver developers can link into hardware that does more, and hardware developers can advertise things that do more and say there's an architectural way to define registers where you can actually have more things supported. Because again, the fixed set of capabilities sometimes isn't enough. People need to be able to do more, and having these things defined architecturally is a good way to do this. And they're very much similar to how PCI devices have extended capabilities. So we've got a kind of a graph here of what an example implementation looks like. It's got a bit of a view of how these things are interacting with on the software. And if you're interested, you can go look at the spec more and kind of look at the software more and see how that works. A brief history of what we did and how we went through this. And again, I'm standing on the shoulders of giants here, of people who've helped to collaborate, because I came into the process a little bit later, but some really great people started on this on version 1.0, and they laid the groundwork. And that's why I'm kind of presenting this to you here. Version 1.0 started off in 2018 and represents a whole body of work to get this to where it is right now. This provides a really good starting point for standardizing an interface because it supports, the basics. It supports getting target devices to software and having an interface, getting transfers with the command response language, supporting SDR mode, HDR, DDR, and ternary modes, abstracting the language for send command, common command codes and CCCs, and basic, timestamping with asynchronous modes, and standardizing how dynamic address assignment's done, and offering 2 different modes for different developers, whether you want PIO mode for very simple devices or DMA mode for devices that want to do more for, direct access to system memory. Version 1.1 is the most current release, and we actually took this and resynchronized with I3C version 1 and 1.1.1, and also basic 1.1.1. We add support for a lot of the optional capabilities, such as grouped addressing. We have support for SETA ASA for broadcast assignment. We added support for CCCs and defining bytes, target resets, because these are important, and more robust error handling, scatter-gather support, and other things that system integrators need to link into a host controller and get better performance, better reliability. We also did a lot of clarifications and bug fixes and did better explanations of how software should be interacting with the host controller and explaining the theory of operation. So, and again, we've got the driver released to the open source community. We're making this available as a key component of integrations, and there are many IPs available on the market today that SoC integrators and designers can put together and say, we now want to integrate with I3C and put this out there. So this does exist, it can be used. But the software work group wants to hear about your integrations, the feature requests, and ways to improve this and take advantage of what we want to do. And as part of that, we're in the process of developing the next version of I3C HCI, which adds a lot of what we call optional normative features for things that other MIPI work groups want to do, and other MIPI contributors are asking I3C to do for them. For example, we have a feature on I3C called dead bus recovery, where a target device can take control back on the bus when the controller is no longer responding. We want to do some other use cases for camera sensors for CSI2 version 4, which is in development. We want to be able to have standby mode for secondary controllers. We want to have optional scheduled commands, which can do periodic polling of I3C targets, and flow control for high data rate modes. But we want to do so in a way that preserves software compatibility and make sure that as you, the application developer, can build on what you already know from previous versions of HCI and go from there. And we're also looking for what version 2 of HCI can do, which is going to be a generational advancement. It's going to build on a lot more new capabilities of I3C, but it's going to require more substantial changes to the definitions. And we want contributors to review this and look at our plans and make sure that we're doing this with an eye towards what's going to work for you. And with that, I'll hand it to Michele, and we'll talk about how to enable power-efficient designs.
Thank you, Matt. So we're going to be coming to the third part of the presentation. Here we wanted to focus on a specific area, which is becoming more and more important with especially for the IoT, and give some practical explanation how I3C can achieve a certain goal. So it's a bit more of a, let's say, application slides. I hope you don't mind that, but I think just to allow you to understand more how things work under the hood. So why it's okay? Traditionally, I3C was targeting sensors which are primarily found in mobile devices, but now with the huge growth of the IoT, there you have, this is becoming very important there, and very often you find that the a big chunk of the application area of IoT is low voltage operation devices running on battery, and sometimes even it's not replaceable battery, which means that there's every single electron that you use, it's important to reach the target lifetime of the device. So how can I3C can help that? Well, let's see in the next slides a few examples. Some things are the most obvious that you would think of, in terms of electrical features of the bus, but there is also other features which are more system-like that you can use to gain power advantage there. So let's say this is a typical, say, IoT device. You have some sensors, maybe external interfaces, a display, comm unit, and there you need to, what you try to do there is that the transactions on the bus not only run at the low power, but it's also very effective, very short in time, because when you keep things going, you need to keep the units running. That means you are using power. So even the fact that the transaction can be completed in a short and efficient way, it becomes important. Another aspect is that maybe they can do some kind of, let's say, power management. You can put things to sleep or in idle mode from the bus without having to resort to custom design features. And I think really helps to integrate and put things together. So let's start, let's say, with the electrical part. As Matt explained, this is a bus working at low voltage down to 1 to 1.2, and we're working to go even lower than that. Keep the capacitance small, because what's really affecting the consumption is the the pull-up values and the capacitance on the bus, because every time you do that, you need to charge and discharge the capacitance. So really the power consumption there, you got three factors where one, okay, you have shoot-through current when you switch, and this is really has to do with the pad design or the IP vendor that's providing. So it's really not under I3C control. The bus capacitance, I say that's something that keep leads short, shows a good thing. And then finally there is the pull down current when you are keeping the value low, and this is really where we concentrated, to optimize the use of this mode. And how do you optimize? Well, first you try to keep the time you are low there as minimal, as small as possible. And then on the I3C, we have the capability to switch from pull up to push-pull mode. So wherever possible to switch to that which is more power efficient. Then I will show you in a second how these things is done. But before I do that, just a recap. The bus can be in three states: the pull up, there is high impedance, and there is also a new thing which you did not find in I2C. If you have something floating, you want to have maybe kind of a soft pull up to avoid that you have floating things and random signals. So the strategy that was adopted there in I2C would say, okay, SCL, we don't need to have a pull up, because the clock stretching was kind of, except in a very, very special case, was avoided. So this is always push-pull. So SCL is running always in a good, efficient way. On the SDA line, this is a bit more complicated because now the controller and the other devices, they need to switch between the different states in a very dynamic fashion sometimes. But this is ultimately, I think it was reached a very excellent result. Let me, okay, this is an example. This would be, let's say, the most common, it's not the only one, but the most common transaction you see on a bus, where you have, okay, you have the start, and then you have the I3C broadcast address, which is mostly ones. And at this stage, you are still in a pull-up mode, but notice that all the bits are high there, so you're not consuming any current. So it's true that you are in pull-up, but you're not consuming any current. I think, okay, maybe you think this is a small thing, but imagine that this thing happens hundreds of thousands of times in a life cycle of device, maybe millions of times, and then really adds up. So this was a very, very clever way. The other thing is that, in that part of the transaction, the bus can be arbitrated, means another device, can pull up the line and try to gain the thing. So if you have a smart selection of addresses, for example, avoiding, you have all the zeros on the first. So there is the addresses are, there are chunks of address space you can assign. So there is a nice set there where you have the first bit, which is 0. So if nobody is claiming, means nobody will arbitrate, and you can go in a fast clock mode. So the rest of the bits, you go very fast. The advantage there that you squeeze this broadcast time really to the minimum, and shortening the time means, running for less time and consuming less current. And then, okay, if somebody acknowledges, if there is at least one device acknowledges on the I3C, then you can switch and push-pull for the rest of the transaction. So all in all, as you see here, that everything was kind of carefully crafted, that you minimize the time you're in this power-consuming slow pull-up mode, because this is needed for I2C compatibility, and then you go into fast mode wherever is possible. Okay. Here you see some energy comparison. Just we put on the last column for just for reference the I2C. You see that the big increase in terms of power use. This is a model with a certain bus capacity and certain pull-up rate and for kilobit exchanged. And you see that there are the different data rates there. The standard data rate is the one which is, let's say, I2C similar. There is a double data rate, and then there are two additional ones which are, the ternary. They use a ternary signaling, and I just noticed that those two are not available under the I3C basic specification. There is also fourth data rate, which is called burst mode, which is really an improved DDR without just a continuous stream of bits with the CRC. On the other diagram, you see that also the raw bit rate is much higher than I2C. As I said before, keeping the transaction short is also a power gain. So not only you're using less energy, but you're doing it faster. So double gain there. So from that, you get that if really the I2C compatibility puts a burden on that, you know, there are certain things. So why not? One of the things. Why not exploit the routing function? So in I3C there is a possibility to have a router that can route messages between different buses, and then you take, let's say, a pure I3C. You have modern sensors that can really spit out a big amount of data. You know, they sample at several kilohertz, so it's very fast. So if you isolate all the I3C, maybe keeping everything short and nice into and this is collected by a local MCU for example, some kind of a sensor fusion processing or similar. Then this the panel I indicated in the red part can run in a very efficient I3C mode, but then you can reach the primary controller and other, let's say, legacy devices there. So for example, this is something that you could not do with other similar sensor buses. And also you keep also that you can still access at a single level, because all the devices behind the router will be seen as a virtual device. So you don't lose any accessibility. So this is, for example, one way to design your system to benefit of the I2C, keep the compatibility and have a low power. Okay, now I have a few more features I'd like to show before we conclude. One is that in I3C there is an activity state. So the controller can tell the other device, look, I'm not going to do anything for a certain amount of time. This activity state timer is currently defined 4 values from a microsecond up to 50 milliseconds. And if you look at the lower two, activity state 2 or 3, 2 milliseconds and 50 milliseconds in modern devices, it's a significant amount of time. You know, you can really put things in idle mode, and you can really save up quite a bit of energy there. Just a note, you know, the activity state is not really, it's not a must, but it's a suggestion. So if a target needs to stay awake for some reason, it can still do. But it will, if it does not have anything peculiar in place, he knows that the controller will not do anything and will go to sleep for a certain period of time. Okay, so then we have another feature that I think also Matt mentioned, you know, the in-band interrupt. The in-band interrupt was initially devised to allow a target to notify a controller that he needs some servicing without having extra wires or anything. But there is some nice little feature in the IBI where you can basically plug some small amount of additional data. Let me show on this next slide. Basically, you have the initial IBI where the target that it wishes to raise the interrupt will pull down the STA line, then the controller will clock, so you'll put his own code and so on. And then there is, after the initial part, you have a so-called mandatory data byte. This is something that is defined in the bus configuration register. So this is some of the registers that are needed in I3C, you know, for the controller to find out all the different aspects. And with the BCR, you qualify the interrupt. There are some fields, some values are already defined, but in the specification there are areas, there are slots of MDBs that are reserved for vendors. So you can really design your application where you can make use of the mandatory data byte. Then you can follow some additional byte. This is also defined in that initialization stage with this specific common control code, the set MRL, the one that I showed here. So just to give you an example, let's say I have a temperature sensor, you know, you have some warnings or there is a danger trip point. So, and I need to service is very, you know, it's very fast. So I raise the interrupt. I say, you know, temperature tripped, And then I send temperature reading, other kind of qualifier alarm. So it's just single shot. You don't need to do a follow-on reads or other complicated things. It's a very efficient way to send small amount of data up to the processor for further processing. So it's a way to exploit the interrupt, the IBI for let's say additional purpose, not generic interrupt. But likewise, another feature that can be used to optimize the power consumption is the hot join. The hot join was defined primarily to allow to connect a device to the bus at a later stage, so you have an accessory or something. But why not use the same feature to put things to sleep? So let's say in this example, I have maybe a communication unit like could be, I don't know, a LoRa that I would need to keep alive only for the short amount of time I need to send some data. So I keep it off for most of the day, and then when I need it, just send up some kind of wake up signal, which could be inbound or outbound. This will be on the design. Then he wakes up, he will join the bus, he will get all the, so he gets its own address, all the bus initialization, and then you can use it and then put it to sleep again. You may say, okay, why don't we just keep it on idle? The problem is that if you keep something on the bus, it needs to do a few things here and there. So it will eventually use some power. By keeping it off and then bringing it back fully functional is probably more efficient way to do it. Okay, so with that, so this is the similar diagram to the IBI. So here it's the target that is a reserved code for the hot join. You notice that it's almost all zero. There is no address below that. So it's really high priority once you wake up, and then you will need to be made functional, assigning dynamic address. Okay, so it just so that concludes this part of the presentation. So believe that IoT not only has a lots of features, but it's very suitable for low power devices, not only because of low voltage support and low power, but also because it's got some interesting functions that can be used to, let's say, have architect a very smart low power design. So and so I think that as more and more sensors and MCUs and things are expected to be on the market, I think really encouraged to look into this. Maybe not told us about maybe new ways to in this area, new smart ways to efficient the power management, other ways to keep it, or maybe bring requests and let us know, about the feedback on this part. So with that concludes my presentation and all the presentations here. We have put some additional information regarding the whole topics we covered. There's lots of material, where to download specs, FAQs, papers, other events. So I give it back to Ian. Thank you.
Okay, thank you, Michele. I think it's actually a second additional information slide that I did add late in the day, because we've got so much additional information, and some of these items have actually only just been published. So I think Tim mentioned earlier on this various application notes, literally just been published in the last few days. So I added them onto the sources of additional information here. Okay, so thank you everyone, Tim, Matt, Michele, for your presentations. Seeing a number of questions have already come through the Q&A panel, and also see that Matt's done a great job and answered some of those questions already. I'll probably just go straight through to the first question that Matt hasn't had a chance to answer yet. It's actually a question on Michele's presentation. So Michele mentioned no clock stretching in SCL. Does it mean that I2C compatible slave cannot signal to I3C master to wait before sending next transaction?
Sorry, okay, but I missed the last part. I don't know if you heard it.
Yeah, so there's no clock stretching in SCL.
Yeah.
Does it mean that an I2C compatible slave cannot signal to an I3C master to wait before sending next transaction?
The clock stretching is only allowed in very specific. We found that it's really seldom used. It's only allowed in very, very specific cases, and most of the time, because most of the controller will run at the speed which is compatible with the I2C. We'll only go to in I3C mode if it's sure that no, as I shown, in the transaction that you only switch to I2C mode where you're sure that I2Cs are not active on the bus. Otherwise, you will run at the speed that will be compatible with the I2C.
Okay, thanks, Michele. Matt, anything to add to that?
I think if the questioner is asking if we need a delay to wait before the next transaction starts, yeah, without clock stretching, I think it's going to be difficult for an I2C compatible slave or target device to really put up something that says, wait, I need to have a gap there. I don't think we have a good solution for that just yet. This is something we need to take and think about in the work group a bit. So,
okay,
yeah.
well, we can take that one offline and we can respond once we've given that some thought.
Yes, let's just do that.
Yeah, let's do that. Okay, let's move on. Comment here about the max bit rate for HDR TSP for being indicated at 40 megabit per second in the slide. 12.5 megahertz, it should be 37.5. Looking at the graph, the bar is under 40, so maybe it's a rendering issue. I don't know if any of the panelists want to comment on that.
Yeah, it's closer to 37.5. It does get a little variable because of the symbol to bit rate conversion.
Okay. Okay, another one about clock stretching. There, if it's the similar question, clock stretching appears to be replaced by clock stalling, timing of which is managed by the controller. Is there any indication of how many I3C host controllers will include this feature?
Not as many. Not as many. What clock stalling is typically used for in I3C, we define clock stalling in specific places, and that's usually either to give the target device a chance to catch up or to allow an ACNAC time to propagate. I think Michele covered some of that. What we see for that is longer clock stalling, all the way up to the maximum in some cases. What we see is that there isn't a lot of controllers don't have a lot of parameters on that. Like say I want to do 100 microseconds or 200 microseconds or 500. We don't see a lot of controllers that have tunable parameters that let the host software stack go in there and change those knobs a lot. And I think that might make it a little difficult to tune that for target devices that need a little bit longer delays on that. Michele, do you have any additional context on that?
No.
Okay.
Okay, thanks, Matt. Okay, so the next one, again from same attendee. In I2C, microcontrollers can leverage clock stretching to delay a host from reading before data is ready. What mechanism is used in I3C to tell when host can come back and read valid data if there's no clock stretching? So again, similar theme.
I think an I2C device could simply just NAC the transaction. Just provide a NAC on their dynamic address, and that's the indication that they're not ready yet. If it's a write followed by a read, and they need time to process that write and have a response ready for a read, the target device could just NAC the read and have that be the indication that they're not ready yet, and then try the read again, and then after a couple attempts, there's a timeout, and say I haven't done that yet. You could also use the get status CCC with some of the additional application reserved bits, maybe bit 6 and 7 to indicate the transaction's in process, or if the transaction failed, you're not going to get a response out of it, and have that be a quick and simple status that the controller could use to ask and say, are you working on this, or did it fall off of the edge?
Okay, thanks, Matt. Yeah, we've got a lot of questions to get through here, so let's keep going through them. So the next one, what could be the max speed allowed? Can we overclock it? It's a rather general question. Don't know if that makes sense. Michele?
Well, I mean, the specification it's 12.5 megahertz. So overclocking, I mean, it's, I don't know, it would be, I'm tempted to say that you do it at your own risk, because some devices may work, but some may not, and then you also maybe they may work at a certain temperature, but they may not work at higher temperature, because it's so it's
I guess it's not really a question we can answer.
Yeah, so it's 12.5 max clock rate. The duty cycle of the clock is flexible, because you don't need to have a 50% duty cycle in order to let's say enjoy the spike filter feature that will make the clock invisible to the I2C devices. But other than that, I'm not. I don't think we can say what happens at faster time. You just try and see what happens if somebody wants to. But I think if a vendor
yeah, okay,
want warranty something different, it's up to the vendor. Yeah.
Okay, so I guess it's clearly defined on the spec what it works at. If you go beyond that parameter,
Yeah.
that's unknown territory. Okay, let's move on. Maybe one for Tim here. Can you explain the different use cases for I3C, particularly referring to the slide that talks about the different groups using I3C, PCIe, sideband, the IEEE 1722, etc.
Yeah, absolutely. So these are works in development. So I've met a couple times with some of the leaders in the PCIe work group. We're trying to get I3C as a sideband bus for use in PCI Express, and the exact uses for that are still in debate within the PCIe work group. So that's why it is a developing technology there. Same with the IEEE 1722. We're just in the very early stages of many of these developments, and so though we're working even, for instance, on A-PHY and PAL, we're still having architectural talks with the A-PHY work group and how we're going to accomplish getting I3C moving over A-PHY. But typically that's what this is we're out there enabling I3C, trying to get it involved in as many systems, on as many connectors as possible. Our thought is I3C as a universal two-wire bus for everything, and so we're just trying to enable as many use cases. And honestly, we know that through getting it out there and having as many people use it, that's how we make the best bus possible. We get the best feedback, and we're able to improve the bus to the best of its ability as well. So Matt, I don't know if you want to add anything. I know you've got some deep workings in with some of these liaison works.
Yeah, I think the cases in development fall into two categories. Number one, how do we bridge I3C and either provide access to remote use cases from further away networks? And I think the IEEE 1722 and A-PHY are the two classic examples of that. And the other ones are, how do we take existing things and bring them into I3C, which is, PCIe sideband, ETSI for Smart Secure Platform, other use cases. So I think you see these kind of fall into two general groups from that point. I hope that explains what the questioner was asking.
Yeah, okay, thank you. So moving on, again, we've got lots of questions to get through. So probably I want to just clarify, does the I3C HCI replace the I3C master?
So an I3C HCI does specify a master or bus controller inside of it that actually is in charge of the bus and sends the commands, gets the responses, monitors the IBIs on the bus, receives those things, and makes those available to the host in a way that is abstracted, that is, has a defined interface. So it does actually include that inside of it. So that is a way to standardize the interface for connecting target devices to an application processor, an MCU, a PCI Express peripheral on a computer, SoC. Yeah, so it does include that.
Yeah, okay. Okay, moving forward, Michele said, question for you. Aside from shorter time on the bus and maybe lower voltages, why is push-pull lower power than open drain? Michele, I think you're muted yourself.
The voice.
Yep, you're there. Sorry, Michele, I don't think we can hear you. No, he's gone on to mute. I'll perhaps pass that one to Matt. I'll make Michele shorts his mic out. So Matt, any views on you from this one?
So The open drain one, I think, has to keep the open drain class pull up engaged all the time. So there's a continuous current sink there within the controller versus the push pull, which is continuously driving low or high all the time.
Okay, thanks, Matt. Michaela, I don't know if you're back. Like we've
lost
Michaela for some reason. Okay.
No.
Okay. A question here about speed and distance competition of I2C versus I3C. I don't know if you've got any kind of comparative figures that we can state with regard to speed and distance. I don't know, Tim, is that one you can cover?
Nothing that I could quote off the top of my head right now.
For speed, I know that in the I3C basic spec, there are some comparisons in terms of different speeds, different scenarios, but at distance, I'm not sure. I guess by distance, they mean line length, I guess. So yeah, maybe we, oh, got all the issues going on connectivity wise here. So let's move forward. Hopefully you can still hear me. Does NACS to host can escalate into host error escalations? Please consider what I3C can have to say. It says come back in X amount of time before next command to this target. I don't know, Matt, if that makes any sense. That isn't quite worded correctly.
It makes sense. I think what we're really getting to is whether your host can handle NAC as a part of its content protocol, or whether it could see a NAC and say, I'm going to stop processing everything and I need you to deal with this immediately. And what we see different I3C controllers, including host controller interfaces, do is they actually do stop and ask software to deal with that NAC and say, is this something you expected? Should I pick up and carry on? You know, what's the next thing I should do? What's the next command on the bus that I need to issue based on a NAC? And if your software driver is responding to that and saying, this is something I did expect, that's fine, you got a NAC, very well, carry on and retry this command again, that's perfectly fine. So if a NAC is part of your content protocol and that's something you're expecting to deal with, your driver picks up that NAC and says, okay, I see you have a NAC there, that was expected, that's perfectly fine, we carry on and we go from there. So really, I mean, if we say, you know, it comes back in X amount of time before the next command, that really is a question of the whole system. That's the question of the controller, the software that's driving it, the bus, the target. All these things have to account for the whole content protocol, the whole expectation of what all these things are doing and working together. So if you're designing the whole thing working together as a system, NACS can be actually a fairly useful part of that. So let's keep that in mind. It doesn't have to necessarily be a complete stop on the bus, the thing has fallen off. You can still use the get status CCC to see whether the thing is responding or not. You can do other, you know, other CCCs or commands to see whether the target still is awake and doing what it's supposed to do.
Okay, thank you, Matt. Okay, another question here about backwards compatibility with I2C. Just a query, just questioning whether we're kind of being misleading. I don't think we'd be misleading, but I guess perhaps we're not being clear enough, maybe. So there's designs on the market today with clock stretching. We believe the claim that I2C works with I2C, we need to be an asterisk involved. I'm not sure.
So there are asterisks.
Whether we need to offer extra. There are asterisks, I know, but perhaps we can offer some verbal clarification, Matt, perhaps.
So those are specified. They're in the document. They're in the FAQ. We do clearly state that clock stretching isn't allowed. This has been clearly stated. If you do need to integrate with I2C devices that do use clock stretching, you can use a bridge device. If it's a must-have and you need that on there, there are bridge devices that can probably handle that, or there should be bridge devices that can handle that. But there's a good reason clock stretching is not allowed on an I3C bus. And that's because to do so would require both the controller and the target to contend and fight over the SCL line. And that's one of the reasons that's not allowed, is because SCL line is almost always driven by the controller in push-pull mode instead of I2C, in which the SCL line is driven in open drain mode. And having that in push-pull mode is one of the reasons that we can get better performance in I3C versus I2C. So we kind of can't have it both ways.
Okay, great. And then one final question in the Q&A session. I think there's some questions in the chat box, which I'll go to in a second. But can you throw more light on practical use case for the RST act command?
Yeah, absolutely. Reset action is a command that actually lets you configure what the target is going to do when you immediately use the target reset pattern after reset act. And this is something we developed in I3C 1.1 and then clarified again in 1.1.1. You actually have some very fine-grained control over what part of the target is getting reset with the target reset pattern in the reset act CCC. You can reset just the peripheral, which is the basic part of the target that handles the buffers. You can reset the whole chip, which is that part plus everything beyond it. And if you have additional parts, you can actually do specific targeted resets to those different domains within a chip, depending on how complex your chip is, depending on how you make use of reset act. If you have multiple targets on a bus, you can send a broadcast reset act that says everybody else no reset, and then send a direct one that says specifically you reset, and then the target reset pattern, so you can do very selective control over which ones of these get reset and which ones don't. And that's an advantage over some of the other defined reset methods that are in I2C or SM bus, which just hold both the lines low for a long period of time, and then every device is supposed to assume a reset's required in that part. Reset act and target reset pattern offer a much better and more fine-grained control over it than those methods.
Okay, thank you, Matt. So I'm just going to look at some questions that have been submitted through the chat box. So one question here about obviously attendee presently working on an I3C slave controller, finding a few things not very clear in the specification, potentially not resolved in the FAQs. How do you suggest they put their queries forward to the I3C working group? I guess requests for clarification, how do they submit them?
Yeah, so we've got a couple options. Sending your questions either to admin at MIPI for non-members or I3C at MIPI email. Those questions will come right to really us, the people on this panel, and we're very active with those questions. We'll get back answers to you, or if need be, we are more than happy to have a conversation with you and help figure out what issues you may be running into.
Yeah, happy to help. So if you're not sure you're a MIPI member or what your kind of membership level is, just go to the admin@mipi.org email address. That'll come through to myself and my other colleagues here in the marketing team, and we do respond to all those messages, and we'll give you the help you need. So another question through the chat window here, asking about synchronous timing control. It says it wasn't mentioned in the presentation. Do we not recommend it?
I don't have a lot of visibility into the usage of synchronous timing control.
I think
so I can't say don't use it.
Yeah, the reason it wasn't in Michele's slide deck is that Michele is just covering I3C basic. Oh, Michele, you're back. I'll let you answer.
Yeah. Sorry, that's a network. Yeah, it's no. I think it's a feature that's very interesting for certain use cases, but it is not available under the I3C basic. And today I think we wanted to focus a bit more on the basic, but I think it's a useful feature that is perfectly, but that's the only reason. And also we had a limited amount of time, so we tended to privilege the features that are available in the I3C basic. Yeah, but it's definitely something very interesting to look at.
Yep, thanks, Michele. So a question regarding hot join, how to handle corner cases. For example, how does the slave know that the bus it is plugged into is actually I2C and it needs to be silent? Similarly, are there many other corner cases?
So I3C 1.1.1 and I3C Basic 1.1.1 also help to clarify some of this, and you're going to see some of these answers in the FAQ. There is actually two forms of hot join. There's the standard hot join for a device that knows it's always going to be in an I3C bus, and there's a passive hot join where the target device waits to see, am I on an I3C bus, and it watches for certain things on the bus, including a recognizable start followed by the broadcast address, which is 7E, which will never appear on an I2C bus. And once it hears those things and listens for that and sees a recognizable stop, then it knows I'm on an I3C bus, and it knows it can actually initiate the hot join request at that point.
Yeah, and you also noticed that I think the hot join say address is it's very low, which has got a high priority, so will arbitrate very easily, and you can get on the bus very easily, you know, without having to risk of collisions and delays.
Right. And one more point on that, that's another reason why a lot of I3C controllers are recommended to start off their transactions with start 7E, then repeated start, and then the address of the target they want to talk to, versus just start and then the address, because that actually helps to continually signal to such devices, you're on an I3C bus, by the way. It just continues to reinforce that.
Okay, thank you guys. Coming towards the top of the hour, I think we can probably just take one or perhaps two more. There's a few more commercial questions coming, which I'll won't cover. We can't sort of offer market insight or talk about specific product implementations. But just focusing on the technical questions here. Question here: how often is timing control adopted? Kaylee or Matt, would you care to take that one? Kaylee. I'm thinking McKaylee's gone again, unfortunately. So, Tim, Matt.
Oh. I don't have a lot of data on how timing control is adopted. I think we'd have to refer to other MIPI contributors to know more about that. What we are hoping for is that the asynchronous mode 0, which is in I3C and I3C basic, is going to see some more adoption. But since I3C basic 1.1.1 is very new, we have yet to see a lot of adoption of that yet. But I think we'll gather some more data and stay tuned on that.
And then I think probably the next, maybe it's the final question, maybe we have one more, but is a 50 nanosecond glitch filter on SDA SCL a must-have for I2C compatibility?
If you want to be able to run I3C transactions at full speed and still keep compatible with I2C, you would need a spike filter. If you don't have a spike filter, you'll have to keep all the other transactions of the bus at a low speed, and then that will be something that those other devices can tolerate. So it's a conditional. It's not a strict requirement, but it does depend on whether you want I3C to operate at full I3C speeds or you want to bring it down to full I2C speeds or not. Without that glitch filter, it does negatively impact performance.
Okay, thank you, Matt. So perhaps one last question and we'll wrap up. Future forward question. Do you see the future going towards 1 volt operation?
We are seeing 1 volt operation, of course, for the sideband bus for DDR. I'm going to guess and say it probably could become more common, but I think that's going to be a specific implementation question for the different use cases that would need it. I think that some of the Etsy smart card stuff might benefit from a lower voltage, but I can't say for sure. Michaela, do you want to offer some insight on that?
Yeah, there was a discussion. At the moment, it's 1.2 seems to be the lowest one, but this was a discussion there to go below even a 0.8. So it might come in the future. Not in this round. I hope you can hear me because I had some network issues here. So it might come actually there as well, because this will be the Etsy thing will be in mobile devices. So the trend is go lower. Yeah.
Okay, so thank you. I think we've reached the top of the hour, so probably need to wrap up. I think there are some questions that we haven't covered. We'll respond to those offline. If you've included your name and company details, we'll get back to you offline. But I think for today, we probably need to wrap up. So thank you, presenters, for joining the session, to Tim, Matt, Michaela for giving great insight. Seeing a few messages here that it's been a really good, enjoyable session for our attendees. Thanks for that. Apologies for the connectivity issues and a few glitches. That's the nature of these live webinars. Hopefully that's made it a little bit more entertaining for the audience as well. All I can do now is thank everybody for attending, and we'll see you on the next MIPI webinar sometime soon. Thanks a lot, everyone.